Hey everybody. So today in this tutorial, what we're going to do is we're going to look at a couple of data sets that have some problems in terms of normality and outliers. And what we're going to do is figure out how to determine whether or not these data are distributed normally and if they've got outliers in them. And then we're going to see if we can fix some of those problems by using a few different types of methods in the different programs. So let's get right into it. Okay, so the first thing I'm going to do is I'm going to load up our Excel file with a data set called RT Data Outliers. And what this is it's a data set that has reaction times from two different groups, RT1 and RT2. And the first thing we're going to do is we're going to evaluate whether or not the data are reasonably distributed normally by using our descriptives. So we just go up to our Data tab, over and select Data Analysis, and we're going to select Descriptive Statistics, and I'm going to select my input range, and that's going to be these data here, all the way down, okay. And it's grouped by columns, and there's labels in the first row, and I'm just going to ask for summary statistics and the output into a new worksheet. Hit OK, and I get a new worksheet. And what we see here is if I look at my skewness and kurtosis, we see I've got kurtosis in both groups greater than 4 in this case. And remember that we said that if we have skewness or kurtosis greater than about 2 or less than 2, that could indicate problems with normality. So if we go back to our data set, we say, okay, what can we do to have a look at how these data are distributed? The first thing I'm going to do is I'm going to create box plots. And the way we do that is we're going to select just the data, not the headers. Select all of the data all the way to the bottom here. I'm going to move over to the Insert tab, and we have a few different chart types. The one right in the middle here, if I hover over it, it says Statistic Chart. I'm going to click on the drop down, and I've got a few different options. There's histograms, but there's also a box and whisker plot. So if I click on that, it creates a box plot for me. I'm going to grab the corner of it, make it a little bigger so I can see, and we can see that there's some issues, obviously, in this data. These are indicating outliers in the data. So what we see here is, interestingly, reaction time shouldn't be very short. There may be, a couple of 100 milliseconds, but something like down around 10 milliseconds doesn't make sense at all. So we should find out what those data points are. So I can see here, if I hover over it, that the value is 16, and this value also is 16. So the question is, what do I do about this? Well, the first thing I could do is just search through my data for those values, 16. So there's a couple ways I could do that. I could just scroll down manually because I don't have a lot of data to look through. Or I can highlight it and find Control F, 16, find next, and it will scroll me down to there. Now, if I close that, I look at this doesn't seem... First of all, it doesn't seem like it's the rest of the data here. This looks like there's a space between it, and that number might be representative, but this is something that's a little bit weird that looks like a calculated number. It's got a bunch of decimal points and one that's 16. Now, I have a sneaking suspicion that this is a mean, standard deviation, and standard error. So I can actually try and calculate those and see if that's the problem that we've got. If I take an average of my data set, yep, 490. That makes me think that the standard deviation is going to be 100 and some odd that was there. 117. Okay, so what that means is these aren't part of the data set. So these are mistakenly added into the data. So what I want to do is simply delete them, get rid of them, and now we can actually look and see on our plot here that what we've done is we've gotten rid of those low values in our data. All right, we'll see a little bit later on what to do about these higher outliers. But let's move on to doing the same thing in SPSS, evaluating for these outliers. So I'm going to open up the same file in SPSS. Okay, so we have this file. It's called rtoutliers.sav. And what we know is we already know that these values are problematic, but we're just going to go through the same process again in SPSS. So the way we do that is we go up to Analyze, Descriptive Statistics, and Explore. Remember, we did this once already. Now I'm going to select my two values for reaction time. I did that by holding down Shift as I selected, and move them into the dependent list. I wanted to display both statistics and plots. And I'm going to click on Statistics and ask for descriptives, and I'm going to click on Outliers. Next, I'm going to click on Plots, and I'm going to ask for not stem and leaf, but histogram, and normality plots with tests. Okay. Now I can hit OK and look at our output that we get. So again, what we see is we've got high kurtosis. Skewness looks okay in this set of data, and reaction time to, again, very high kurtosis. It provides me with extreme values, so the highest and lowest 5 of RT1 and RT2, and I can already see that there's some issues in here. And it provides me with a test of normality. Now, Shapiro-Wilk is usually the one we're going to use. The Shapiro-Wilk test is a test of normality that's best for smaller data sets, but can handle data sets up to about 2,000 samples. If you need to go any higher than that in terms of your sample, you might want to think about using the Kolmogorov-Smirnov version. Okay, so what we see is our test of normality shows that both reaction time 1 and reaction time 2 are significantly non-normal. If this is significant, it means they're not normal. So I can look at my histogram, and what we see is we've got outliers at the bottom and at the top. A QQ plot that we've talked about, which is quantile. If it is reasonably normally distributed, it should fall along this diagonal line. We see that it doesn't. It's got these high points in the bottom and low points in the top. And if we scroll further down, we see a box plot that's generated. And what this does is it has our outliers that are highlighted with circles and extreme outliers that are shown as asterisks or stars. And nicely, right beside it, it gives us our case number, so the row in which it's located. So I can look down here and say, okay, I've got some very low values at cases 54, 53, and 56. What's the problem here? It will also show me the same thing for reaction time 2. And I see it's 53, 56, and 54, again, are problematic. Okay, so now what we've done is we've been able to do our tests of normality and look for outliers and problematic data. Let's try doing the same thing in JASP. I'm going to open up the same file in JASP. Okay, here's our reaction time data. Again, the only thing we need to do here is we need to run descriptives, and we're going to select reaction time 1 and reaction time 2 as our variables. And what we see is it gives me my descriptive variables, but I want some more statistics than that. So I'm going to click on the drop down. Now I can ask for various things here. One of the things we can ask for is in the distribution, I can see that I can ask for skewness and kurtosis and a Shapiro-Wilk test. That's great. So we can see that I've got a Shapiro-Wilk value and the p-value, which is less than 0.001. Again, saying that these are significantly non-normal. The other thing I can do is look at my skewness and kurtosis, which show similarly large values to what we've seen in the previous program. So what I want to do is click on plots. And here again, I can ask for similar plots to what we've asked for in the other programs. Box plots, and it generates those. And I can ask for maybe a QQ plot as well if I want. And I can scroll down and start to look at these values. And what we do is we see that there's some values that are outliers at the low end and values that are outliers at the high end. So there's no real easy way to deal with those like in Excel, but in JASP, all we do is I can click on the side here and we get back to our data. I can just double click on this data and it will open it up in Excel where I can do the same thing that I did to it just previously. Okay, lastly, let's do the same thing in R. So I'm going to open up R. Okay, so this should be the file that we've seen before and been working on. So the first thing we need to do is import our data, and that will be the RT data outliers. So let's import a data set from text. And it's going to be RT data outliers.csv. I'm going to open that. I'm just going to call it maybe RT datas _ out. And it does have headings, and that gives me RT1 and RT2 in my data frame, and then I'll import that. Okay, so now we see we've got our RT1 and RT2. I can scroll down. We see we've got a lot of NA values in here, so we might have to clean this up a little bit more too. So I guess the first thing we may want to do is run our descriptives on this data. So if I go back here, I'm going to select one that I used before. Maybe this one here. That gave me stat.desc, and what I got was tests of normality with this one as well. So remember, for this one, we need to have the library paste.cs in here. So I'm going to just load up that library. So if I scroll down to find it, there it is, and click on that one. Now I'm going to just copy this, and in fact, I'm going to copy the whole thing and put it down at the bottom. What I'm going to do is give myself a comment. If I use the hashtag or number sign here, it will make whatever comes after it as a comment. So I'm going to say load library paste.cs, just so it reminds me each time I need to run this one. The other thing that I want to do for this one is I remembered that this gave me scientific notation values. So I'm going to use options scipen equals 999. So now what I'm going to do is attach the correct data frame, and that is called RT data _out. I can just click on it there, attach the data frame. Then I want stat.desc, and what is the variable I want? RT1. Now I can run this and see the output that I get. Okay, so I get all of my values. Looks like my skewness and kurtosis are quite high. They're not exactly the same as what we saw in the other programs, but I suspect that's because we have some NA values and weird values that we need to get rid of. Okay, so I can do the exact same thing if I want to on RT2 and run that. And we see again, I get this high value for kurtosis, and skewness is actually quite high here as well, 1.18. Okay, and my tests of normality, we can see, are very significant in both of these cases. So we know that our data are significantly non-normal and there's some problems in the data. So just like in the other programs, we may want to look at this using a box plot right off the bat. And the easy thing we can do with R is just use a box plot function. So I'm not even going to put it into my regular script. I'm just going to type it in the command window. So box plot RT data _ out. And we see it creates this nice box plot for me. Now, if I want, I can copy that and paste it in to maybe this set here. So it'll just run it each time. And we see we've got these box plots, but the problem is I don't know where these data points are. So there's a couple more commands that I can do to get that. It's a little easier if you just take your data back out into Excel and then re-import it once it's cleaned. But I'm going to show you just in case you need to do it inside R. So the first thing we want to do is we're going to create a new variable called out. And this is just going to, you can call it whatever you want, but I'm just going to call it out. And into out, I'm going to put boxplot.stats, and we can see that we've got all this other stuff in here, but I just want RT1, and then I need $out. Now I'm going to just do the same thing. For RT2. So maybe I'll call this out1 and out2. The other thing I can do if I want, I can do this descriptives on RT1 and RT2 at the same time. Now, if I just run all of this, again, I've made a typo. It should be boxplot.stats, not sats. So let's get in here. Happily, it's very easy to fix. Just put a T in there, run this whole thing again. Okay, now what it's done is it's giving me two new variables here, or two new objects up here, and it's just provided me with this data again. Okay, and now in order to find out where those are, I need to use another command. And it is which, I have to tell it which data frame we're talking about. So it is RT data underscore out. And for this one, I need to tell it which column to use, RT1. I need to use a little command %in%, and then C out1. Okay, now I know this is a little bit cumbersome, but this is just the way that you can get these values out. And once you've got it typed in once, you can just copy that again. So now I just need it for RT2, and it's out2. Now if I just run this set of commands again, what we see is I've got everything I had before, but now it's also given me which data values or which spots in that list of data are my outliers. And I could go in and I could either delete those manually or try and figure out where the problems are exactly. So if I went into this RT data and I can see, okay, so it's at case number 12 in RT1. It's 670. Okay, that looks like it's fairly high. It's maybe that value there. And I can scroll down. I see the last one, 56. Right, that's that value, 27. I can start looking into these values to see what the problems are. Okay, so now let's go back to the start, and we're going to find out how we start to deal with our outliers in order to fix our problems with normality and outliers. Okay, so we had already talked about doing transformations, so you can go through that and see if that makes any difference to your data and maybe rerun the stats, look at the skewness and kurtosis and see if that changes. One of the other options we can do is start by trimming our data. So what we can see here is I've got my set of data here, and how do I trim it? So the first thing I'm going to do is I'm going to get in and I'm going to sort my data from smallest to largest. We do that by just selecting the whole column of data, clicking on Sort and Filter, and click on Sort Smallest to Largest. It asks me if I want to expand the selection. that would mean that it would tie this value to this one. And I don't need that. I know that these are two different groups. I don't want to do that. So I'm going to continue with the current selection and sort. Okay. I'm going to do that with column B as well. Sort and filter, sort smallest to largest, continue with current selection, sort. Okay. Now, what we can see here is that I've got my lowest values and my highest values here. If we wanted to simply do trimmed means, it's very simple. I know that I've got 50 values. It's row 51 because there's a header. So I've got 50 values. A 10% trim would be taking off 5 values from the top and 5 from the bottom. So what if I just simply did that? And I just selected these data points. Maybe I don't want to just delete them, but I get rid of them out of that graph. And I move that, and I take these ones, and I move them over. Okay. Now what we see is we actually have no more outliers in our data, which is pretty interesting, which is good as well. Okay, so I'm going to undo those two things. Okay, that's good. The other thing I could do is replace outliers. In this case, its value is 670. I want to scroll down here. That's this value. So the one that's the next lowest would be 640. The idea would be for Winsorizing to replace any values above 640 with 640. So I can actually just drag that down. Okay. The other way we do that with this one, this is only 950. So I'm going to replace anything above the value below 950 with anything with that value. So it's 850 is the next highest one. If I replace those all with 850, that changes values. Again, I don't have any further outliers. Then we can rerun our descriptives and see if we have significant skewness and or kurtosis left in the data. Okay, so now let's use SPSS to clean up our data in a slightly different way. I'm going to open up the data file in SPSS. What we can see here is we've got our RTs. And remember, we just realized that these are all bad values. So I'm just going to select them and delete them all. So they're gone now. Now, one thing we can do in SPSS that is a little bit more difficult in Excel is we can transform our values to Z-scores very easily. So remember, we had gone up and gone to Analyze, Descriptive Statistics, and if we select Descriptives, and I select my two variables, put them in, I have this option here to save standardized values as variables. And if I click that and hit OK, what we see is that it creates Z-score values for each of these. So Z of RT1 and Z of RT2. Now with that, I can actually use another function in SPSS called select cases. So if we go to data, scroll down to select cases, I'm going to look at, right now all cases are selected, but I'm going to say if condition is satisfied, if Z-score RT1 is greater than, let's give it some value like 2.5. That would be really unexpected. They would have to be fairly strong outliers to be greater than 2.5 Z-scores away from the mean. Hit continue and OK. What we see is it crosses out all those variables in ZRT1, right, that have Z-scores less than what I've specified. So we see at line 35 here, we see we've got a Z-score in RT1 of 3.5. So I might want to go in and either delete that value or replace it with something else. But let's just simply delete anything that has really high Z values. And again, there's another one, 940. Okay, so that looks like that's all of the ones for RT1. Let's do the same thing for RT2. So back into data, select cases. If, now I'm just going to change it to ZRT2 instead this time and hit continue. Okay. And now I'm going to search for these rows. Okay, 34 has a 4.81 z-score. So let's get rid of that one. Okay, and any other ones? No, that looks like that is it for those. Okay, now go back into data, select cases, and select all cases now. So it's done that. Okay, having done that, I'm going to go in and I'm going to run my descriptives again. So I'm going to go into descriptive statistics, explore RT1 and 2, and I'm going to select statistics, give me outliers, okay, plots, I want histogram, normality plots with test, continue, and okay. Now, what we see is I've got 47 cases left in both RT1 and 2. My skewness and kurtosis for RT1 looks a little bit better. It's less than 2. RT2 looks much better, 841 and 1.165. It's highlighting some of what it would call extreme values, but it's just the highest and lowest 5. My tests of normality still show for the Shapiro-Wilk that I'm significantly non-normal. Again, that's probably because reaction times are typically skewed. And we can see that in the histogram. I do have in RT1 some of these values outside. But again, my normal QQ plot is starting to look a little better. It's getting closer to this line. The same thing can be said for RT1. Now has a couple of outliers that are a little bit different. Remember, we took those out, but it can recalculate z-scores again. So if I go down and think, okay, why don't we do this in an iterative process? That means let's do it again. So I'm not quite as close to normality as I would like. So I'm just going to select my Z, my other Z, my filter, get rid of it, and we're going to run that process again. So I'm going to go into Analyze, Descriptive Statistics, Descriptives, and save my standardized values as variables. That will give me my new z-scores. And now I'm going to take our data again, and I'm going to select cases that have greater than 2.5 z-scores. So select cases. If, let's do for RT1, is greater than 2.5, and let's see if we have any. Scrolling down, looks like I've got one right here. I'm going to delete that value. Looks good. Oh, and one there at level 12. Now let's do one more. I'm going to Data, Select Cases, if ZRT2 is greater than 2.5. Okay. And again, we're looking for cases that do have that. Looks like we've got one at 3.20, so I'm going to delete that as an outlier. Okay, so that's now gotten rid of my z-scores. I've gotten 1, 2, 3, 4 out of RT1 and gotten rid of 1, 2 out of RT2. Okay, so let's run our descriptive statistics on this data now. Before I do that, I'm going to select all cases again. Okay. Analyze, descriptive statistics, explore. I've got all of this set up already. All I have to do is hit OK. Now what we see, again, skewness and kurtosis have come down again for both values. Now my tests of normality are not significant, and that's giving me more strength that I think that my data can now be analyzed fairly. And our QQ plot for RT1 looks pretty good. My box plot doesn't show any outliers. The histogram for RT2 looks pretty good. My QQ plot for RT2 looks pretty good. And I don't see any outliers in my box plot. Okay, great. So what we could do is see that some of the options are better to do in Excel, some are better to do in SPSS, or at least easier. But you can do them both. It just takes a little bit more work in one versus the other. JASP doesn't really give you the option of doing the cleaning because all it does is it opens up the data file back in Excel. So it would be a matter of doing what we've just done in Excel for that. So let's move on to R next. So let's open up our file in R. And remember, this is where we had left off. And remember, we saw that at the bottom there are these problematic values that we need to get rid of, and also a bunch of NA values. So how do we do that first? Well, the first thing I'm going to do is I'm going to create a new numeric list of the things that I need in this. So the first one will be RT data column 1. And into that, I'm going to put RT data underscore out column RT1, and I'm going to use rows 1 through 50. And you can see it's created a new object up here called RT data C1 that's a numeric of 50 length. Now I'm going to do the same thing. I'm going to just use my up arrow, copy that, and make it RT data C2. And it's going to be RT2. And now I've got that as well. Now I can combine those into a data frame using data.frame. And it's going to be RT data C1, comma, RT data C2. Okay, so what we can see is it printed that out. I forgot to put it into its own new object. So I'm just going to, into that, I will go RT data underscore out2 is that data frame. And we can see now it's created this new data frame that's only got the first 50 observations in it from there. So now on this data, we can do our transformations if we wanted, like we've shown you before. And maybe it might be easier to do that in Excel, but there are various different things we can do with it. One thing I want to show is a few things that we can do in R that are a little bit unique. So the first one, it's going to need a package called desk tools or descriptive tools. So I'm going to ask it to install a package called desk tools, that one, and install. Okay, now that that's installed, I'm going to load the library. Go scroll down here to descriptive tools. Okay, now that's loaded. So one of the tools we can use with this is a trim function. So I'm going to go back into our script and I'm going to pick out the thing that I need at this point. So let's just use something like this where I'm attaching a data frame because I need to build some new stuff. So here we're going to use, and we're going to pull open data frame RT data out2. Okay. So the first thing I want to do is I want to create a new object that I'm going to put some trimmed values into. And I'm going to create a new data frame called RT trim. And into that, I want to put, I have to use data frame command, trim, and then I select what do I need from RT data out to. Well, it's RT data C1. Okay. RT data C1, comma, 0.1 will give me a 10% trim mean. Now if I run these commands, you'll see that now I've got a new data frame called RT trim, and it's one variable, and it's got 40 values. It means it's taken 5 off the top and 5 off the bottom of the 50 that I had before. Okay, now it's got a weird name. We can fix that up later. Now I'm just going to do the same thing, but I'm going to add a new column. Now because this exists already, I can create a new column. I'll just call it RT2 data frame, and it's going to be RTC2. Run this, and it should just add that as a new column in this data frame. Now I run that, and we see RT trim now has 2 columns or 2 variables, 40 observations. We see, there we go. So now we've successfully done a trim of both of those. Okay, now we're going to use another function called Winsorize, and I'm just going to maybe just copy this whole set again. And we'll just do the same thing, but instead of making it RT trim the first time, I will call it RT win data frame, and it's going to be Winsorize data C1. And my default is going to be, it's going to Winsorize anything that is below the 5th percentile or above the 95th percentile, and just make them the same as all those other values. Okay, so the top values and the bottom values will be the next highest within 95 or 5% intervals. All right, so if I run that, see, I get a new object called RT_win, and it's got 50 observations. Remember, we didn't trim anything. We've just taken those values and we've made the bottom ones the same, we can see here, and the top ones the same. You can't see them because they're not sorted in that way. Okay, and we're going to do the exact same thing for RT_win. I'll give it a new column, RT2, and we'll do the same thing with RT_data C2. And run that. And so now RT_win should have 2 columns again. So now what you can do is you can go ahead and run your descriptive statistics on these new data frames, on the trimmed data and on the RT Winsorized data, and see how they differ from the original data that had some problems in terms of normality and outliers. The last thing we're going to do is we're going to try to run a bootstrapped t-test. The way we're going to do that is we're going to need to load another package, and it's called mkinfer. So I'm going to install that package. It's called mkin. There it is there, mkinfer. And install that package first. Okay, now that it's downloaded, and I'm going to click on it to load the package. Okay, now that we've got that package loaded up, what we need to do is have a data set that we can try this out on. And remember, for doing t-tests, that it needs to be in a long format. So what we're going to do is load up the same data, but just in a long data format. So we're going to import the data set, and I'll find it here. RT data outliers _long. So I'm going to open that, and it's got headers, and I'm just going to call it RT data _outlong. Okay, and import that. Looks good. I've cleaned up some of my other data sets that I didn't need, and now here I've got 100 observations of 2 variables, and that's our long data set that's got group 1 and group 2. Okay, so if we go back into here and we look at our script, we're going to take a independent samples t-test example that we used. Now that was just right here. I'm going to copy it. I don't need everything in here, but I'll paste it there, and I'm just going to get rid of my measures of effect size. Now remember, we need to attach the correct data set. So it's RT underscore data out long. Excellent. And then I'm going to describe by, it's going to be RT as a function of group. I believe that is correct headings. RT as a function of group. Okay, so if we run our t-test on that, oh, I didn't put that in the right spot either. So we're going to put in RT, that was just the description, the descriptives, RT as a function of group. Okay, now let's run it. Okay, so we end up with the 2 sample t-tests, and I have a p-value of 1.18 times 10 to the negative 13 with a t-ratio of 8.6318. Now, I don't expect that running a Bootstrap t-test is going to make much difference, but let's do that. The only difference is, instead of t.test, is we run boot.t.test. Remember that we need to have that mkimfer in there. We run this entire set, and what it does is it gives you the results without Bootstrap, which is the same as what we had here. And then it gives us a bootstrapped p-value. So again, in fact, it's even more highly significant, if you want to call it that. 2.2 times 10 to the negative 16. Okay, so finally, let's go back into SPSS and see what happens and see how we run a bootstrapped t-test in SPSS. So I'm going to open up SPSS, and I've got the same data file opened up. It's RT data outliers long.sav. Note that this one's the SPSS data format, but you could import the CSV if you want. Either way. The way we run it is simply the same way as we would do a normal t-test. So we go to Analyze, Compare Means, Independent Samples t-test. Now we put RT into our test variable, and we select our grouping variable as groups 1 and 2. Okay, we've got that. And then we have this button that says Bootstrap. I'm going to click on that. And we have a checkbox that I'm going to select, Perform Bootstrapping, and it asks me for the number of samples or the number of bootstraps. The more you put in here, the longer it's going to take. I'm going to leave it at 1,000, and I assume this will be done in maybe about 5-10 seconds. Okay, so if I hit Continue and then click OK, it will run the t-test bootstrapped for me. So we can see here it's running the t-test, and it's doing multiple tests of that, so it's taking some time, isn't finished yet. There we go, popped up. So if I scroll down, what we see is it gives me my independent samples t-test that we have here, and our t-ratio of 8.632, which is what we saw before. And our significance is less than 0.00. And I could double click on that and find the values. What we also have right below it is Bootstrap independent samples t-test. And what we see is it gives me a significance two-tailed at 0.001. Now, if we wanted to calculate the actual t-ratio that is associated with that, all we need to do is take our mean difference and divide it by this standard error here. And then that way you get your bootstrapped t-ratio as well. Okay, so that's a lot of stuff to have gone through, but try those out and practice a little bit using those different functions to be able to change your data so that it can be more normally distributed and that you don't have out of control skewness or kurtosis. And then you can also try running some bootstrap t-tests in both SPSS and in R.